SwayamPrabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory as a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 6th lecture on Marine Renewable Energy Systems course offered by Swayam Prabha at IIT Gandhinagar. I am Prof. Chandrasekaran, heading the Department of Maritime Engineering at IIT Gandhinagar. In this course, we are going to discuss in detail about the analysis, design and development as promised in the first lecture on the course contents. In continuation to what we discussed in the previous lectures, this lecture we will talk about the important aspects of frequency domain analysis. Friends, we are now trying to understand the primitive modeling of wave energy converter to achieve, or you can say obtain, an appropriate geometry One can wonder why we should talk about appropriate geometry. Simply point observer can be used as a standard defined geometry to harness wave energy. Friends, that is not the case. Please visit back the previous lectures. The geometric design is essential to address the C state specific requirements of the design, wave directionality of the design, water depth where you want to install, and of course, are you going to go for floating wave energy converter or fixed wave energy converter. So, the geometry must enable first the stability in terms of hydrostatic and hydrodynamic. In both cases, we say the stability can be achieved if you design the system with enough recentering ability. So, therefore, friends, the whole design of successful wave energy converter circumscribes with choosing an appropriate geometry. Therefore, we need to have a primitive modeling of this wave energy converter to achieve or to obtain a successful geometry or arrangement of different point observers in series or in parallel or a wave field or a wave train, so that we get the maximum efficiency. Secondly, friends, most importantly, you would recollect that wave energy converters are one of the special class of design where the fundamental frequency of the system is set to match with the dominant peak frequency of the exciting force, that is the waves. So, generally when you look at the design of structural systems, we never design the system for this band, because it is expected that the system will fail and undergo maximum response and causing failure to the system if this condition is met. But incidentally, in wave energy converter design, this is the condition at which we will design the system, so that the maximum response of the device would enable me to harness the maximum energy content of the input wave. So, when I am looking for a design which is on this kind of questionable bandwidth and this kind of different perspectives, I cannot go for a complete design at one shot. So, I have to go for an iterative design. To start the design with, I have to go for a primitive modeling, the numerical modeling, where I will do it in frequency domain approach. So, if you look at the block diagram which helps me to plan the frequency domain modeling tool, which is a high-end modeling tool for frequency domain analysis or approach for primitive designs of wave energy converters. I insist the word primitive design of wave energy converters. So, I am looking for a modeling in frequency domain. I can use ANSYS Aqua, I can use VAMIT, I can use NEMO. So, here we are not debating about the comparison or efficiency or convenience and usability of any software. We are only saying I can use any modeling tool for primitive design of the wave energy converter. However, in this course you will learn that we will be using extensively the numerical model based on ANSYS Aqua tool as an example, but that is not the case where we are promoting or we are not accepting the remaining competitive software for designing this. I am only illustrating an example of taking this as a tool to show a primitive design of the model. So, now the input to this model will be on the left hand side. The output what we will extract from this model is on the right hand side, which is required for my further modeling and design of an accurate system of wave energy converter. So, friends, you heard it correctly. The primitive model what we are discussing will not be and cannot be accurate because there are certain parameters which needs to be tuned to get the maximum efficiency. For example, let us recollect once again a very important task before we start understanding this block diagram. Let us say I have a system the system is connected to the seabed and the interface of the wave with the system has got to be harnessed, and we say that will be done by something called power takeoff mechanism. Power takeoff mechanism essentially works on damping applied to the system. Now, to obtain this damping required to harness the energy of the system, I need to know the response of the system for a given wave condition. So, then I have got to tune an appropriate power takeoff mechanism to this response condition, so that I harness the response characteristic of the system to power. So, friends, please understand, the wave energy harvest is not directly obtained from the waves. Waves encounter a system and the system responds to these waves, and that response in different degrees of freedom is harnessed and then connected to the grid for electric generation. So, therefore, PTO design becomes a hub of the whole problem. Now, the PTO cannot be chosen until I have the complete response characteristics of this WEC design. Therefore, I say frequency domain will help me to get the capture width ratio, the absorbed power from the system for a chosen linear PTO. So, initially I may assume a simple linear power takeoff system, a virtual model, fit it to this. Friends, whatever I have chosen may not be completely appropriate for my design. I will then redesign the PTO for this condition. To start the iteration, I assume a linearized PTO for the beginning. Then I fix the PTO to the existing WEC design, subject this to wave action virtually in the numerical model, get the responses, and then from the response I try to redesign the PTO. For the redesigned PTO, I again conduct this. So, it is going to be a big cycle of iteration, friends. So, to start with, the primitive design of WEC is generally and comfortably done using frequency domain approach. So, in this approach, the device parameters, what you obtain from a 3D solid model, then the hydrodynamic sea state conditions as water depth will be given as an input, in addition to the mass, inertia, center of gravity and center of buoyancy of the chosen wave energy device, which will be an input to this frequency domain model. You also have to give the linearized mooring model, because this is going to be moved to the seabed. So, we initially start assuming this as a linearized model. You can also have a catenary model, you can also have a complete floating system where the flotation is controlled by dynamic positioning systems, etc. We can all do that, but that is all in the later stage. In the primitive stage, we assume a linearized mooring model. Then, as I said beginning, we also assume a linearized power takeoff system virtually, which may not be the best suitable system for the chosen WEC design, but we assume, because if we do not assume this, I cannot obtain the power requirements which is based upon the response of this system. So, friends, response will not give you energy. Response need to be converted through PTO to get energy. Okay? So, this conversion is the second stage on wave energy harvest. The first stage is encountering waves, make the system to respond. The second stage is from the response, I harness this to power. The third stage, of course, will be converting this mechanical power to electric power using generators. Okay? Of course, this part we will not focus much in this lecture. Of course, my colleague at IIT Gandhinagar has a parallel course where this is being expressed in detail in the full course content. So, I would request that you should also learn this course in parallel to get a full idea about the whole wave energy harvest systems for renewable energy sector. So, then we also give the input from the wave energy resources as frequencies and directions of wave at a specific sea state. Then I do a complete modeling. Then I obtain the excitation force, the radiation damping and added mass. Friends, these are all very important input for my PTO design. Okay? And if you do not attach a PTO to this, you cannot obtain this. Okay? So, there is an interlocking, that is a strong coupling between this provision and this output. So, if you do not provide this, you will not get this output. Okay? Then the system responses are tracked in terms of response amplitude operator, and you will also try to obtain the mooring forces and PTO forces, which are an extracted outcome from the numerical model in frequency domain. Then you will also now compute approximately the absorbed power and the capture width ratio of this model. So, to improve the efficiency, you have to increase the power, absorption and capture width ratio to be increased. As we said in the previous lectures, the capture width ratio can be even more than 100% in multi-body dynamics. So, therefore, to obtain all these design parameters for further improvement on the design, I need to first run a primitive model in frequency domain approach. So, that is what we explained in the previous lecture, and we continued that for your understanding in this lecture as well. Now, the question comes, when you start doing the frequency domain approach, what will be a serious handicap or what will be a serious constraint which can cause error in obtaining the results? That is a good question. Let us now ask about what are the constraints or let us say catch points in frequency domain approach when we start doing a primitive design of wave energy converter. Okay, let us ask this question. The foremost task of the accuracy in analysis essentially comes from meshing, because in numerical analysis meshing becomes a very important aspect. Therefore, the major task is meshing. Now, if you have a too dense meshing and thinking about it's a primitive analysis, you may not require to waste that computational effort on making this model. If you have a too loose meshing, you may miss out certain important factors which can be design control parameters of the WEC model. So, you have to judicially select the meshing size to have decently accurate answer from the chosen WEC model. Therefore, the accuracy and simulation time depend upon the number of elements in the mesh. Okay? I think you all will agree, those who are aware about the numerical studies, you can easily tell that this is a very well established statement which you can always agree and accept. If you look for multi-body dynamics, let us say multi-body wave energy converters, let us say you have series of floats, series of point observers interconnected or connected by a single spindle, then you have multi-body invoked in the analysis, then the number of elements will obviously increase. Therefore, there has got to be a trade-off between the number of mesh elements and the anticipated accuracy. Okay? This trade-off can be generally advised based upon my experience, which I will show you later with some design examples on developed wave energy converters, patented and Indian grant technology transfers. So, based upon my experience on numerical analysis, I could say that if you have edges, if you have complex contours in your wave energy converter profile, then go for a mesh size which is twice the body size. Okay. The rest of the part you can have coarse mesh. Friends, this is not a golden statement. This is based upon my accuracy and my experience on arriving at certain primitive designs of wave energy converters which I experienced during my research front, I am giving you this trade off. So, this can be a useful hint for you to start with. Okay. Having said this, having understood what would be the block diagram for high end frequency domain approach, the question now comes is, what softwares can I use, commercial packages can I use to do this? Friends, we are not at IIT Gandhinagar advocating any specific, recommending any specific software. It all depends upon the ability and the comfortability of the user. However, the common packages available, common commercial packages. Okay, all these packages also have educational version, what they call educational release at a compromised price. So, if you are an education institution, if you are looking for your computer center, I think you can approach these organizations for an educational version. Of course, there will be some limitations in the mesh size and the element size in running the model, but for research purposes it is sufficing the idea. Okay. The commercial packages which are generally used in frequency domain approach for VEC modeling primitive are, let us say, VAMIT, ANSYS Aqua. Aqua is a module which runs as an add-on on ANSYS, and you can also have something called NEMO. Okay. These are a few commercial packages which are very comfortable to use for VEC designs in frequency domain approach. There can be many of them which I may not be even aware, but please do not quote me that these are the only thing which we are recommending in the course. These are only examples which we are citing for your comfortability. Okay. So, these packages solve the boundary value problem using panel method. This is otherwise called as boundary element method. The package solves the diffraction and radiation velocity potential by applying the source function and solve them, find the corresponding strength on the submerged surfaces, the excitation force matrix, the added mass matrix, the damping matrix, the pressure field variation and response amplitude operator, which are all the output of this, okay, can be obtained from these models using boundary element method solver. Okay. However, Aqua has an added advantage. Okay. Let us see what is that. In compared to other software, the ANSYS Aqua advantage is it uses graphical user interface for modeling, simulating, and it has got very limited pre-processing tool. Okay, these advantages makes Aqua more comfortable to use in primitive design of VEX, but it does not mean that others cannot be recommended for these primitive applications at all. So, we will discuss examples related to specific version V19.2 for using this in frequency domain approach. Of course, the results what we will be demonstrating in this lecture are all done with the license applied to IIT Madras, where I am also a professor in ocean engineering at IIT Madras. Therefore, the results what we show are all licensed to the researchers who carried out the studies under my supervision at IIT Madras. Okay. So, friends, the software package, name, brand does not matter. What we wanted to know here is what is the basis on which they work. Okay, we are looking at that. So, in that context, let us see this specific slide. So, if you look at the slide which is on the screen at this moment, this gives me the frequency domain specific workflow based on ANSYS Aqua. Okay, this is a frequency domain workflow as shown in specific one of the softwares. Okay. So, if you look at carefully the segments, the stages at which the results are obtained in this specific package, we have something on a workbench where you will start developing the device geometry and all associated parameters of installation depth, wave climate, directions, etc. See states in this specific level what we call as Aqua workbench. Once the model is prepared in workbench, you transfer or export this model to something called Aqua line. Aqua line will receive information for wake frequency and directions where you want to run the model, and the device geometry and its parameters becomes an input for 3D diffraction and radiation analysis in Aqua line, which is actually done using boundary element method. The output from Aqua line segment of this software will give you the Froude-Kraloff force, which is hydrostatic. It also gives you the added mass as an output. It gives you, most importantly friends, the diffraction and radiation damping which are required for designing the power takeoff system. Okay. Friends, it is hypothetical, but still I want to make the statement, without making a detailed numerical model in any package, you will not be able to obtain the diffraction and radiation damping analytically. You have to make a model in any one of the numerical tool to obtain this. You may ask me a counter question, why do we need this? If you do not have this, you cannot design an appropriate PTO for the WEC. If you do not have a PTO, you are only designing the first stage of the wave energy converter. You are not moving to the second stage, because the harness does not happen from the wave input. The harness happens by tuning the response of WEC to the wave input to a mechanical system, what we call as power takeoff system. Okay, to design the power takeoff system appropriately for your WEC, for your input parameters, C states, etc., you need to know these values, which otherwise cannot be obtained without any numerical tool. It can be any tool as we suggested, but you need a tool to do this. So, once we obtain this, we move this model forward to something called Aqua Librium analysis. There we attach now a virtual PTO and a mooring line to the system. How do you design this? Now, you already have the friction and radiation damping values. Based on this, you can design a virtual PTO which needs this as an input in the design and attach it to the system, and of course support this with a mooring line as well. Then you do something called equilibrium analysis and stability check. That is why it is called Librium, equilibrium, no? Aqua Librium. So, here you do equilibrium or recentering analysis and try to assess the stability of the chosen system. Okay. So, the output from this analysis could be the static and dynamic stability of the chosen WEC system. Now, this can also be interestingly a feedback loop. Later I will explain that. So, once this is done, it is taken to the next stage where we do Aqua FER, where we perform frequency domain analysis completely for a different wave spectra, for which you are going to install the wave energy converter. Then once you do this, the wave energy converter responds to the wave spectrum, you get something called response spectrum, we can also obtain something called response amplitude operators, which is actually the ratio of response amplitude operator looks like the ratio of amplitude of response to wave amplitude over a frequency range. Okay? So, you get a curve. So, at any frequency, what will be this ratio? So, this is amplitude of the system to amplitude of the waves. So, if you multiply the amplitude of the waves to the system to this number, you get the amplitude of the response for any wave, right. So, once you get the response amplitude operator, you get something called aqua GS results. This GS results now can help you to change the damping coefficients for your PTU. PTU actually is to be designed based upon the damping ratios. We already said that in the previous lectures. So, to do that, you need to obtain the feedback results from here, change and input this, rerun this and so on. So, there is a small iteration happening here. Without changing the primitive designs, you can keep on doing only the PTU designs, alteration and try to get the maximum harness and the condition for which the maximum harness can happen. So, in general friends, the broad output what you get from frequency domain approach will be a standard geometry of the VEC what you wanted and the C states at which this VEC can work, and of course, appropriate PTU what this VEC can be fitted to. So, I get this output as an extracted results from the frequency domain approach of the primitive design of wave energy converters. Okay. Having said this, since the frequency domain modeling is based on linear potential wave theory, all of the above statements are valid because the forces from various sources acting on the body are balanced. Okay. So, since the frequency domain approach is based on linear potential wave theory, I can say the forces acting on the wave energy converter are balanced by the force balance method, which is actually the Newton's second law of motion. Okay. Now, what are the forces we are talking about here? The forces what we are talking about here comprises of 1. The non-viscous forces, 2. The viscous forces, where the drag and friction drag are part of viscous forces. The boundary layer friction effects are represented by the friction drag. The friction drag represents the boundary layer friction effects. Which are usually small relative to the form drag. Okay. This is what we call as a form drag, which comes from the geometric form. Friction drag comes from the boundary layer. Usually, the friction drag in terms of its value or magnitude is far lesser with respect to the form drag. Okay. But still, you will get this value in this analysis. However, the form drag will keep on increasing with the cross section of the structure. Okay. The form drag keep on increasing with the size of the structure. The structure we consider is the wave energy converter. Since we are dealing with the potential theory, the viscous effects need to be ignored. So, potential theory cautions us to ignore the viscous effects. Non-viscous forces include hydrodynamic forces, other than the viscous force. Okay. Which includes the moving force, PTO mechanism, because the PTO mechanism will also have a force, no? And the surface force on the wake. So, they all will be computed and categorized under the table non-viscous force effects. We need them to design the wave energy converter in a more effective manner. Now, the wave potentials and the wave energy converter response are generally represented in a complex term in frequency domain. So, the results are now represented in a complex term in frequency domain. Okay. Let us say the wave potential is phi. Phi for a monochromatic wave, which can be represented as a combination of temporal and spatial functions. So, I can now represent phi, which is a function of spatial and temporal components, as Re phi hat of x, y, z, t, e, I, omega t. I am only looking at the real part. Okay. So, let me call this equation number 1 for this lecture. Of course, remember the number is not continuous from the previous lectures. So, be very careful when you start quoting these equations from different lectures. So, now phi hat is a complex wave potential. Omega and t are frequency and time representation. So, all the boundary conditions now are to be represented in a complex form. Now, for simplicity, let us take a single degree of freedom system WEC. Let us take or let us consider a single degree of freedom system WEC model. Okay. Now, we want to develop the equation of motion for this to do an analysis. So, all the forces acting on the WEC with its response are to be represented in a complex form, which will be a time dependent parameter and complex amplitude. Therefore, I can represent the displacement of the WEC as x of t, which will be Re x hat of omega E I omega t. The velocity and acceleration can be further given as x dot t, which is Re of I omega x hat omega E I omega t, and acceleration is a further derivative of this, which will be x double dot t, which is Re minus omega square x hat omega E I omega t. Now, for Newton's law, the complex equation of Weck of a mass m can be written like this. So, let us apply the force balance equation on the Weck. So, I can now say it is minus m omega square x hat of omega E I omega t can be F total of t E I omega t. The total force F total represents all hydrodynamic forces acting on the Weck. Okay? So, F total represents all hydrodynamic forces acting on the Weck. Okay? But it excludes the viscous force. With external forces induced by the PTO and the mooring lines. Okay? The external forces, the viscous force, the mooring line force, they are all excluded in this F total. The right hand side of this equation 5 is a complex value. Okay? So, now I can say the hydrodynamic force which is F total can be classified as or into excitation force and radiation force. Let us see how do we classify this. Let us see this. The equation of motion which is now expressed as a force balance equation which we saw in this slide, okay, which we saw in this slide, can be now detailed the right hand side force like this. So, the equation of motion has got two terms. One is the fluid force, other is the non-fluid force. The non-fluid force essentially arises from the power takeoff system and the mooring lines. The power takeoff system depends on the passive damper and the spring attached to the system. Therefore, we provide something called virtual damping and virtual stiffness. Remember that virtual term is being used because there is no actual PTO available at this moment for the design. We are now arriving at the design of the PTO, right? So, we are fictitiously, we are randomly using certain virtual damping, what we call CPTO, and certain virtual spring stiffness, what we call KPTO, which are all functions of operational frequency attached to the PTO to the system, and they arise from non-fluid forces. In addition, the wave energy converter is position restrained by mooring line. For simplicity, let us assume that we are using a point observer. It is position restrained by a mooring line. The mooring line will also have a linear mooring force Fm. It will also have a linear stiffness K and will have an unstretched length dl, inextensible cable. Okay, mooring let us be an inextensible cable. So, unstretched length dl, and it will have a stiffness which is AE by L. For a linear spring, you will also have the mooring characteristics. So, put together both of them will add to something called non-fluid force, whereas the fluid forces will have applications from hydrostatic and hydrodynamic. Hydrostatic refers to the buoyancy and gravity forces coming from the system, whereas hydrodynamic forces are divided as wave excitation force and radiation force. Remember that, friends, when a body is subjected to waves, the body will oscillate. When the body oscillates, it produces radiation around it, right? We saw that in the previous lecture. So, there are two kinds of forces now, the wave exciting force and the radiation force generated from the system. So, the wave exciting force will give rise to fluid Krylov force and diffraction force, okay, whereas the radiation force will give rise to added mass and radiation damping. So, we get all these four outputs from the hydrodynamic forces as a result of this component, and the fluid force will comprise of both of them added to this. So, F total does not include the viscous forces. Okay. Having said this, let us summarize now what we learnt in this particular lecture before we move forward to the next lecture. Let us say in the summary, in this lecture we discussed about details on frequency domain approach, or say modeling of wave energy converter. We already accepted that this is useful only for primitive design of wave energy converter. The primitive design requires an input from the power takeoff system, which we do not have an idea about this moment. Therefore, we assume something called virtual PTU, linearized, run the model and get the data and then redesign the PTU properly. Okay. Therefore, we call this as a primitive design. So, then based upon the model what we propose, the challenge what we said was the meshing. We have an idea how the meshing can be generated for approximately better results and so on. So, friends, stay connected with this series of lectures on this course, Marine Renewable Energy System Design, Analysis and Development, offered by Maritime Engineering Department at IIT Gandhinagar in the SwayamPrabha portal. Thank you very much. Namaste.